Alright, Math 125, Statistics. Today we're going to start talking about Chapter 6. Chapter 6 is entitled Normal Probability Distributions. I'll abbreviate it just to save time. And Section 6.2, which we're going to talk about today, is standard normal distribution. Okay? Alright, before we start talking about the new stuff, I want to look back at Chapter 5 just a little bit. Chapter 5 was entitled Discrete Probability Distributions. And we're familiar with the number of boys and 4 births and the probability of 4 successes and 6 trials, etc. In those discrete probability distributions, the values of our random variable were what they call discrete. For example, if you're looking at x being the number of boys in 3 births, we could fill in the probabilities, but I won't bother here. The discrete means that the values of x are not on a continuous scale. So let me write that down. The discrete in discrete probability distribution means that the random variable values are not on a continuous scale. In other words, x could be 1, x could be 2, but x couldn't be anything between 1 and 2. Right? Discrete in mathematics land refers to values being separated, singular, discrete meaning, in essence, not connected, disconnected. Alright, now in Chapter 6, our random variable values, our probability distributions, will be referred to as continuous probability distributions. A random variable in this case might be something like this. Let x be the speed of a car. And the speed of a car can be on a continuous scale anywhere from 0 to 65 miles per hour. And there are infinitely many values between those limits because the number line is dense. Or I could let x be the weight of an adult male. And theoretically your weight could be anything from 0 to infinity. Well, what we're getting at here is we can't use a list or a small table like we did in Chapter 5 to just assign probabilities in the continuous case. There's just too many values. If I try to make a list here and indicate the probability that x is 10 miles an hour or 50 pounds or whatever, there's infinitely many values of x. Oops, sorry. So I can't list them all. Write that down. Infinitely many values. Right? So we can't use a small table or a list in assigning probabilities for continuous random variables. I'll write that here. We can't use a list to assign probabilities in the continuous case. Alright, well, if we can't use a list like we did in Chapter 5, what are we going to do? Well, to compute or assign probabilities in a continuous probability distribution, what we'll do is this. Well, we'll take a curve that represents the distribution of values in our experiment, and our random variable is now on a continuous scale. What I can do now is, once I've assigned what they call a probability density function, if, for example, I'm looking for the probability that x is between a and b, I can use techniques of calculus to compute the area under a curve between any two limits of x I desire. So what I'm going to do is say this probability is the total area under your curve between A and B. And we'll use calculus to construct that value, that total area. But of course, calculus is not a prerequisite for this course, so don't be scared. What we're going to do is use our calculator to compute that needed area in continuous probability distributions. Alright, so what we're going to do is start talking about normal distributions. That is the title of Chapter 6, Normal Probability Distributions. There's some things I want you to know about normal distributions before we go on to the standard normal. Well, the first thing we should know is that a normal distribution is symmetric with respect to the mean. And what I'm getting at here is there's going to be vertical symmetry in the curve about the mean value. Also, a normal distribution is bell-shaped. Alright, so actually a normal distribution is defined rather formally by a formula that I'm not going to hold you to. It's on page 250. It looks something like this: y equals e to the minus 1/2 power times x minus mu over sigma squared divided by sigma times the square root of 2 pi, where of course mu and sigma refer to the mean and standard deviation of the distribution respectively. Now don't run away. We're not going to use this formula in this course. I just wanted to show you where this bell-shaped curve comes from. Rather simply is this: if x has a normal distribution with some unspecified mean and some unspecified standard deviation, the distribution of x values is going to look like this. It's going to be bell-shaped, symmetric with respect to the mean. So we can see the bell peaks at the population mean, wherever that is. And the standard deviation is kind of hard to pictorially interpret. Don't lose sight of the fact that this bell-shaped curve really just means this: there's not too many scores piling up on the low end. There's not too many scores or measurements or values piling up on the high end, but most values in a normal distribution lie within a neighborhood of the mean, and that is a mathematical term, neighborhood of the mean. Okay? So think of this as an envelope that kind of connects the tops of a histogram. You could think of it that way. Most importantly, remember the total area under the curve, and this is called a probability density function. The total area under this PDF function is of course equal to 1, representing 1 unit of available probability in any given experiment. Okay? Alright, so normal distribution, bell-shaped, and symmetric with respect to the mean. Alright. There are many, really infinitely many normal distributions. If I draw a real number line there, I could have a tall, skinny, bell-shaped distribution of scores. That's supposed to be symmetric. I'm doing the best I can by hand here. That peaks at some mean value. Say it's a mu sub 2 is the population mean for that distribution of scores. I could have short, fat, bell-shaped curves, and I could call that mu sub 1, meaning this bell-shaped distribution, this wide bell-shaped distribution, peaks at the population mean of mu sub 1. Alright, what characterizes the normal distribution is the mean and the standard deviation, not surprisingly. Normal distributions are uniquely characterized by two things. Let me write that down. Uniquely characterized by two things: the center and the spread, namely the mean and the standard deviation. Okay. Alright. One particular standard, I'm sorry, I almost gave it away. I did give it away. The one most important normal distribution is the standard normal distribution. And that's the title of section 6.2. Standard normal distribution. Well, the first thing a standard normal distribution is a normal distribution, but with a particular mean and a particular standard deviation. A standard normal distribution has a mean of 0 and a standard deviation of 1. And we reserve the letter Z to indicate a normal distribution that has a mean of 0 and a standard deviation of 1. Alright, so I can easily sketch a picture or a graph of distribution of Z values. I'll just draw a range of possible values, and I draw a bell-shaped curve indicating the peak would be at 0. Remember, the center of a normal distribution is always at its mean, and the mean here is 0. That's not a 6, that's a 0. Okay? And the standard deviation of 1 is kind of not so easy to pictorially illustrate. Let me ask this question. Before I do that, let me remind everyone the total area under the curve is, of course, 1, indicating my 1 unit of available probability in any experiment. Alright, so this horizontal axis really represents all my possible Z values. Anything from negative infinity to positive infinity, in theory, is possible, and the population mean of Z values is always at 0. Alright, let me ask this question. Suppose I've got a random variable Z is a normal or bell-shaped distribution with a mean of 0 and a standard deviation of 1. Let's say I want to find the probability that Z is between 1 and 2. Find the probability that Z is between 1 and 2. Well, what I can do, And I suppose it always helps to draw a picture. Alright. The horizontal axis represents all my possible z values. The mean is always at 0, so the bell peaks at 0. And I want the probability that a randomly selected z value is between 1 and 2. Alright, so what I need to do is find the total area under this z curve between 1 and 2. Alright, now we can use a table in the book, in the back of the book, and if you want to use that process, you might want to read up on it on page 255 and beyond. But I suggest to you it's easier and maybe quite more efficient to use the TI-83 or 84, and I'm going to introduce a new command here. It's called the normal CDF command, C standing for cumulative distribution function. Alright, so basically we're accumulating all possibilities in this example between 1 and 2. Alright, let me show you how to access this command and use this command in this particular example. We want the probability that z, a randomly selected z value, is between 1 and 2. Right, that is our goal. So what I'll ask you to do is on your calculator, hit the second button, the gold second button, get to the distribution menu, which should look familiar, and I believe it's the second one on that list. Let me check. Second normal CDF is the second command on that list. So select and enter to call up that normal CDF command, and the syntax is for a left bound and a right bound for your given z values of interest. So for this problem, I would want to call up the normal CDF command. Well, 1 would be my left bound, 2 would be my right bound, and if I punch that out and hit enter to evaluate, I get a 0.136. So a very easy way to compute standard normal probabilities without using the table in the back of the book. I'll show you how to use the table in a face-to-face class, maybe run through 1 or 2 examples of that, but for the most part we're going to be using the calculator to grind out probabilities of this type. Okay? Alright. How about, let's say z, again, is a standard normal. How about if I ask the probability that a standard normally distributed variable is greater than 1.5? Now, let me draw a little picture here. Alright, there, z represents this, again, this horizontal axis represents all possible z values, theoretically up to infinity. If I want greater than 1.5, well, if I draw 1.5 here, I want all this area for z values that are really unbounded here between 1.5 and infinity. Now, there's no way to enter infinity directly into our calculator. There is a little bit of a workaround that our author gives us. What I can do is say this is the same as the probability that z is between 1.5 and infinity. And what the author asks us to do is a kind of workaround for using infinity, or entering infinity. I would plug in this value, 999999. Alright, so we'll take the author's advice here. This is our calculator's approximation for infinity. And if I punch this out to evaluate, I get a probability of 0.067. So the area under the standard normal distribution curve between 1.5 and infinity is 0.067. Do another example. How about the probability if that z is less than minus 0.5? Again, that's what I seek. Well, less than means left of. We're still in a standard normal distribution here. Remember, z is automatically means standard normal. Peak at 0. Minus 0.5 will then be my right bound because I want the probability that z is less than minus 0.5. Alright, so I'll use my normal CDF operator. Remember, hit the second button, distribution button, and then the second item on the list is normal CDF. And as you might expect, our approximation then for negative infinity is going to be negative 9999999. Our right bound will then be minus 0.5, and if I punch that out, I get 0.309. Okay. Alright, the book talks about a couple of examples. I also want to talk about here. Example 3 on page 255. Let me see if I can turn there and read it to you over the cloud here. You might want to get your book out and read along. The Precision Scientific Instrument Company manufactures thermometers that are supposed to give readings of 0 degrees Celsius at the freezing point of water. Tests on a large sample of these instruments reveal that at the freezing point of water, some thermometers give readings below 0 degrees and some give readings above 0 degrees. Alright. Assume the mean reading is 0 degrees Celsius and the standard deviation of the readings is 1. Alright, so we got a standard normal here. Also assume that the readings are normally distributed. If one thermometer is randomly selected, find the probability that at the freezing point of water the reading is less than 1.7 degrees Celsius. Alright, so what we got here are a bunch of thermometers. It's 0 degrees Celsius outside. It's a large group of thermometers, so we've got a large group of readings. We'll say all the thermometer readings will be indicated by the variable z. The book tells us this distribution is normal. And the mean temperature reading is 0 degrees Celsius, and the standard deviation of those thermometer readings is 1 degree Celsius. Alright, so one of these thermometers is randomly selected. Find the probability that this randomly selected thermometer is less than 1.27 degrees Celsius. Alright, you get the picture. It's 0 degrees Celsius outside. We've got a large group of thermometers. Some thermometers read 0 degrees, some thermometers read higher than 0, some thermometers read lower than 0. We want the probability that the randomly selected reading is less than 1.27. Alright, standard normal peaks at 0 always. 1.27 is here, and I want this area under the standard normal curve, the z-curve, left of 1.27. Okay? So I'll plug in my normal CDF command. Again, my lower bound here technically is negative infinity, but I'll put a minus 9999999 to approximate negative infinity, and then 1.27 will be my right bound. And if I punch that out, I get 0.898. Alright, so hopefully everybody gets the picture regarding these thermometers. There's a couple more examples referring to all these thermometer readings, so keep those fresh in your mind as we go on. Let me get another screen. Let's look at example 4 on page 256. Again, we're talking about thermometer readings. It's 0 degrees outside, and I want the probability that a randomly selected thermometer would be greater than minus 1.23, or would have a reading greater than minus 1.23 degrees Celsius. Of course, I'm going to use my normal CDF command. Greater than minus 1.23, well, greater than means to the right of, so my left bound would be minus 1.23. My right bound technically would be positive infinity. So I'll plug in 999,999 to approximate positive infinity and punch it out, and I get 0.891. Alright, exercise 5, also on page 256, also refers to the thermometer readings that have a standard normal distribution. I want the probability that a randomly selected z-value, a randomly selected thermometer reading in this example, is going to be between minus 2 degrees Celsius and 1.5, positive 1.5 degrees Celsius. Alright, no infinities here, so I claim it's normal. CDF, minus 2 is the left bound, 1.5 is the right bound. Couldn't be simpler, really. And hence I get a probability of 0.910. Okay. Alright, so we've done 4 or 5 examples of finding probabilities given z-scores. What I want to do now is work it backwards. And by that I mean this: finding z-scores or z-values from known areas. Let's look at example 6 on page 258. Alright, still working with the thermometers. It's still 0 degrees outside. We still have a large group of thermometers. Some read high, some read low. Use the same thermometers from example 3 with temperature readings at the freezing point of water that are normally distributed with the mean of 0 and a standard deviation of 1. Find the temperature corresponding to P sub 95, the 95th percentile. So, let me show you what they're getting at here. Again, Z is a normal distribution with the mean of 0 and standard deviation of 1. That's by definition. They want us to find P sub 95. And the book clarifies this and says this is the temperature that separates the bottom 95% of thermometer readings from the top 5%. Let me write that down. Separates the bottom 95% of thermometer readings from the top 5%. That's what the 95th percentile does. Probably best to draw a diagram here. Z is a standard normal. The mean is 0. If I want the score that separates the bottom 95% from the top 5%, I'm going to exaggerate a little bit just for clarity's sake. I'm going to claim it's there. Right. If I believe this is the location of the 95th percentile, the area to the left of that value is going to be 0.95. In other words, the probability of being less than that value is 0.95, and the area to the right would be then 0.05. Right, how are we going to find this value? Well, again, we could use techniques of calculus, but it's not quite so easy, and calculus is not a prerequisite for this course. So I'm going to use kind of a backwards operator on our calculator. It's called the inverse norm. The inverse norm operator on our calculator. Okay? Now the syntax of inverse norm, if you're using it regarding a standard normal distribution, I want to plug in the area, the known area to the left of a particular z-value that I'm looking for, and that command will spit out that 95th percentile I seek. Well, of course, the 95th percentile is going to cut off an area of 0.95 to the left. So how I would find this command, well, again, you've got to go to second button, your distribution menu, and the inverse norm command. I believe it's third on the list. All right, and the syntax for this particular problem, I plug in inverse norm. 0.95 is my known area to the left, and I punch that out and execute, and I get a z-value of 1.645. So I claim the 95th percentile of a standard normally distributed variable is going to be 1.645. That's the value I seek for this example. Let's do one more example, and we'll call it a day. This is example 7 in the book on page 259. It says, using the same thermometers from example 3, same scenario, find the temperatures separating the bottom 2.5% and the top 2.5%. Alright, I'm going to illustrate this pictorially here, easier than using percentile notation in this example. Again, I'm exaggerating the size of the tail areas here just for clarity's sake. I claim this is the value that cuts off the bottom 2.5%. That means the probability of being less than that value is 0.025. And I can easily use my inverse normal command to find that value. Similarly, on the top, I claim this value is going to cut off the top 2.5%. In other words, the probability of being greater than that value is 0.025. Alright, so let me go to my inverse norm command, and I hit second, distribution, inverse norm, and punch in 0.025, and I get a value of minus 1.96, I'll call it. And it makes sense that this z-value, this needed z-value, is negative. Anything left of 0, of course, will be negative, and the distribution peaks at 0, of course. Now I could do a couple things at this point to find this upper value. Well, I could say by symmetry, this should be the opposite of minus 1.96, which would be 1.96, and that would be valid. Or I could punch it out directly with the inverse norm command. But remember, you have to plug in your area to the left as your input for the inverse norm command. So I've got to figure out the area to the left. Well, if I've got a right tail of 0.025, that means my total area to the left of that upper z value is then 0.975. Alright, so I hit inverse norm 0.975, and indeed I do get 1.96. So either way is fine. You could make a symmetry argument in this problem or do both values directly using the inverse norm command. Alright, we'll call it a day. Next time we're going to talk about non-standard normal distributions, and we'll still be using the calculator quite a bit then. So we're hitting the 35-minute point, so this concludes section 6.2 online lecture, standard normal distribution.